Well, hi, good morning. I'm Inés Pereira, and I come from the Geological Environmental Group from the University of León. And what I'm going to explain today is a little bit about iron mineral mapping in Sierra Minera de Cartagena. So, this study area is located in the, in the southeast of the peninsula, the Iberian Peninsula, and is characterized by, it's characterized by a semi-arid Mediterranean climate. In this, we have a really dry summer, and the precipitation are concentrated almost in autumn months. But this is a really irregular rainfall pattern, because in these autumn months, precipitation is not well distributed. It's concentrated just in a few days, as we can see in this climatogram of September 2019. In one day, we had all the precipitation for that month. Okay, so if we join this climate with a former mining district in which we have tons of mine waste accumulated in our study areas and that are really easily erodible, and also a scarce vegetation cover, which cannot act as a protective factor, what we end up with is that every time we have a torrential event, we have a really huge sediment relocation, like in this torrential event of 2019, which is representing this precipitation. So, in this sediment relocation, what we have is mine waste disposals, because they are distributed along the headwater areas of the basins. And then they erode and travel and end up in the Campo de Cartagena, which is an agriculture area that is really flat. So it's where these mine waste are precipitated. So these mine wastes, among others, are composed by iron oxides. So we use the same technique as Ruth in this study. So we use spectroscopy. Why are we able to use this method? Because these iron minerals have electronic processes that are reflected in the spectral curve. And they have, all of them, a reflectance feature and one absorption feature that can be detected through remote sensing techniques. So iron minerals have this characteristic, but we have different kinds of iron minerals, like jarosite, hematite, or goethite. And even though these three minerals have the same features, their maximums and minimums, as we can see in this image, are not located exactly in the same wavelengths. So if we have a sensor that its bands are in these places, in these maximums and minimums, we will be able to map the three minerals in different and differentiate them. And we can do this with Sentinel-2, because its bands are located in these maximums and minimums. So we want to map these three minerals. Now what are we going to do? For our methodology, we use Google Earth Engine, and we use the level 2A Sentinel-2 images, with this meaning reflection values at the bottom of the atmosphere. We choose 4 different precipitation situations that we will explain later, and we choose one image for each one of these precipitations. We have our collection of 4 images, and we apply some masks. We apply a vegetation mask, a water mask, and a build-up areas mask. So we will not have that much noise in our image. With these 4 mask images, we look for a good member which is a representative spectral curve for each one of our minerals, which was hematite, goethite, and jarosite. And with a spectral angle mapping classification, we end up with a distribution map of these 3 minerals for the 4 meteorological situations. And last, for the worst scenario, which was Adana, that we will explain later, we crossed the data with the land uses map so we could know the affected land uses. Okay, so why did we choose these 3 minerals, goethite, hematite, and jarosite? It was not only because our sensor was able to map them, but it was also because they are telling us a little bit different information. So all of them come initially from the same mineral, which is pyrite. This mineral has an oxidation process, and depending on what happened in our study area, we will end up with one of these minerals. So if we have an acid environment, like around 3 of pH, we will end up with jarosite. If we have a pH around 4, we will have goethite, and if we will have a little bit more basic pH, we will have hematite. So we will know about the pH in our study area. But also we will know about the time that has passed since the last precipitation event. Because as time goes, jarosite is usually transformed into goethite, and as time goes, goethite is transformed to hematite. So we will have a lot of information with these three minerals. So knowing this, which precipitation events did we choose? So we choose a little bit different precipitation situation. In the first one, we choose Adana. This is a Spanish name that is corresponding to a really huge torrential event, as we can see in this precipitation record. Then we choose a torrential event that it is recognized as a torrential event but was really low. It wasn't as big as this one. Then we choose a dry season in 2021 after the summer in which we didn't have any precipitation. And lastly, we choose an event that had moderate precipitation, but they weren't considered as a torrential event. So we did 4 maps for these 4 situations. The maps that we end up with were these ones. So in all of them, blue corresponds to hematite, green corresponds to jarosite, and red corresponds to goethite. Let's see the first situation. We have the dry season. In this situation, we can see that hematite is the mineral that is the main in the situation. We have a little bit of goethite in this area, but almost no jarosite. Why do we have this? We have this because in this situation we have oxidation situation. So hematite can be here. And also, as we saw before, goethite and jarosite are transformed into hematite as time goes since the last precipitation event. And now we are in the dry season. So that's why there is no jarosite and there is not that much goethite. Then we can see the moderate precipitation. In this one, we can see that hematite is less present than in the previous image. This is because we don't have oxidation processes in this moment because we have water, we have moderate precipitation. So oxidation is not really good in this moment. So that's why hematite cannot be as present as before. But on the other hand, goethite has a really huge presence because of the redox situation. We have alternating redox situation, which is really good for goethite to be present in the area. But the same as before, we almost now have jarosite. Why? We will expect in this situation to have jarosite because we did have a precipitation event, but in this case, it wasn't torrential. So in our water flux, the concentration of mine waste wasn't that high because the precipitation weren't that strong. So as we didn't have a high concentration, the pH wasn't as low as it should be to be able to form jarosite. So we didn't have an acid pH. Okay, let's go to the next situation. We have the torrential event. Now what we can see for hematite and goethite is quite similar to the moderate precipitation event, but in this occasion, we can start to see jarosite. Because as we said before, in this occasion, yes, we have torrential event, so that's why it can be formed jarosite. The concentration of mineral waste in the water flux was high enough. And last, we have the Dana situation. In this case, the image is a little bit tricky because the previous image were taken just after the precipitation event, but in this one, we had to wait 3 weeks in order to get this image because the previous one had clouds. So that's why there is a lot of hematite, even though there was a torrential event. But this is just meaning that it was a really huge precipitation event. But in this one, what we can see is that there is a lot of jarosite. Okay, so if we see this data also in a table format, what we can see and get is that jarosite is mostly present in torrential events. Goethite needs precipitation in order to be formed because of the redox conditions. And hematite is mostly present after oxidation process. Dry season and in the Dana. We have to remember that the photo was taken 3 weeks after, so the oxidation process has already started. Okay, and just to finish, we said that we were crossing the data of one of the events, the worst one, with the soil land usage map. And we can see this in this image. So what we can see is that hematite is mostly affecting agriculture land uses. And in this case, hematite is not a toxic element, but in this context, we know that hematite is usually accompanied by lead and by zinc, which can be affecting the croplands in this area. So it would be good to study a little bit more of that. And also we can see that goethite and jarosite are mostly affecting scrublands and the drainage beds. This is because this area are the areas where water is accumulated for a longer period of time. So the redox condition is better for goethite and jarosite. And also, to finish, I would like to annotate that jarosite, in this occasion, is telling us that we did have an acid minage drainage. So that should be studied for the future. And with all of this, thank you all.